This video is going to cover 1.7 from AQA A-Level Chemistry, Oxidation, Reduction and Redox Equations, focusing on oxidation reduction. The video is going to cover ionic equations, simple half equations, combining half equations, and definitions of oxidation, reduction, oxidizing agent, and reducing agents. Oxidation and reduction are really important terms in chemistry, and they've been around for a very long time. Now, historically, oxidation was the addition of oxygen to a substance, and reduction was the removal of oxygen. Now, this was very common for the reduction of iron ore. So here's a picture of iron ore. You can see the red colour that comes from iron oxide, which is often called rust. And the iron oxide was mixed and reacted with carbon, often in a blast furnace, and produced carbon dioxide and pure iron. And here's a picture of iron being used for girders. Now, in this reaction, if we look at it, the carbon is gaining oxygen, which means that it is oxidized, and the carbon has undergone oxidation. Now, reduction is the opposite process, so the removal of oxygen. And if we look at this reaction, the iron loses oxygen and has therefore been reduced. It's undergone reduction. The modern use of the terms has moved on a little bit, and we can use the terms oxidation and reduction for reactions that don't contain any oxygen. For example, 2NaBr plus Cl2 forming 2NaCl plus Br2. Now, before we can look at oxidation reduction in modern terms, we need to consider the ionic equation to check what chemistry is actually happening. Now, an ionic equation is where we break down a full balanced equation like this, and we look at the ions involved in the chemistry and look at exactly what is changing. So if we look at NaBr, NaBr is an ionic compound comprised of Na plus and Br minus. Now we can work those out because sodium is in group 1, so loses 1 electron, bromine is in group 7 and gains 1. If you need a reminder of simple ions, I'd suggest you go away and have a check on that now before you move on. So in this equation we have 2 NaBr, so therefore we have 2 Na plus and we have 2 Br minus present in this chemical reaction. Now this would likely be in aqueous conditions, so we wouldn't have NaBr, they would break apart into Na plus aqueous and Br minus aqueous. The Cl2 doesn't break apart, that remains as it is, so that's the chemical formula of the chlorine in this particular reaction. On the product side, we've got 2 NaCl. Now again, that's an ionic compound, so we would have 2 Na plus and 2 Cl minus, and then we have Br2 at the end as well. Now if we look at this chemical reaction, we need to compare the left and the right, the reactants and the products, and look at what species we have. Now if we do look at this, we can see that we have 2 Na plus on the left, and we have 2 Na plus on the right. Now chemically this sodium hasn't changed, it's remaining as a sodium ion both before and after the reaction. We call these spectator ions, species that have chemically remained unchanged during the reaction. So what we do for an ionic equation is we ignore the spectator ions, and what we have is the ionic equation for this reaction, which is everything but spectator ions. 2 Br minus plus Cl2 forming 2 Cl minus and Br2. Now our reaction between Br minus and Cl2 is a redox reaction, and that is a reaction where reduction and oxidation occur in the same reaction. We can look at how that happens. Now, redox reactions actually involve a transfer of electrons. This is where we come into our modern usage of the terms reduction and oxidation. And if we look at our reaction a little bit more closely, we start off with 2 Br minuses, individual bromide ions that have an extra electron compared to a bromine atom, and we have chlorine gas that's present as a diatomic molecule. Over the course of the reaction, the bromide ions give their electrons to the chlorine, which breaks apart to form chlorides. Now if we watch that reaction again, the bromide ions that were present at the beginning lose their electrons, so 2 bromide ions lose 1 electron each, 2 overall, to form bromine, and the chlorine gained those electrons to form 2 chlorides. Now this is a picture that you might remember from GCSE. This is an oil rig, and this helps us to work out what processes are actually going on when we've got this movement or transfer of electrons. So OILRIG stands for oxidation is loss and reduction is gain of electrons. So applying OILRIG to bromide and chlorine in our reaction here, we can see that the bromide is losing electrons, and because oxidation is loss, that means that bromide is oxidized or has undergone oxidation. And reduction is gain, so because the chlorine is gaining electrons, Cl2 is reduced or undergoes reduction. So what we're going to do is we're going to take this ionic equation for the reaction we've been looking at, and we're going to form 2 half equations to show us the chemical processes that are going on. Now the 2 half equations combine to form the ionic equation, and you can go either from this ionic equation to the half equations, or from the half equations to the full ionic equation. Both ways. Now a half equation is just that, it shows half of the chemistry that's going on in a chemical equation. And each half equation looks specifically at one chemical. So in this reaction, we have 2 bromide ions that react to form bromine, and we have chlorine that reacts to form 2 chloride ions. Those are the 2 halves of the chemical processes that are going on. But at the minute, they're not correct. Take a second to have a look and think why. Now at the minute, these are not chemically balanced. And the reason for that is that although we have 2 bromines on both sides, 2 bromide ions and a bromine molecule, if we look, we've got charges. We have a -2 charge because we have 2 negative bromide ions. But on the right hand side of the equation, we have a neutral bromine molecule. Now mathematically, that doesn't make much sense. If we were to view the arrow as an equal sign, mathematically -2 equals 0 is completely incorrect. Now to solve half equations and get the charges balanced, we have to think a little bit mathematically using negatives only. So how can we solve this mathematical equation if we can only use minuses? Well, what we do is we put -2 on the right hand side. -2 equals 0 minus 2, mathematically balanced. And what this does is it tells us where the electrons go in our half equation. Because we've put a -2 on the right hand side, we have to put 2 electrons on the right. So our half equation is 2Br minus forms Br2 plus 2E minus. See if you can do the one for chlorine. Now charges wise for chlorine, because we have a neutral molecule, we have chlorine being 0 on the left, and on the right hand side we have 2 minus charges, so we write that as -2. Now again, check this mathematically, 0 equals -2, that isn't right. And if we were to try and solve this using only negatives, we would put -2 on the left. 0 minus 2 equals -2 is mathematically correct. And that shows us that our electrons need to go directly above where we put the -2, and that we need 2 of them. And there we have the 2 half equations that would combine to form the ionic equation for the reaction. Now what's really important to see here is that we have 2 electrons being produced, and then we have 2 electrons being gained. The electrons must be balanced. However many electrons are produced or lost by one species, the same number has to be gained by another. Now that we have a basic understanding of reduction and oxidation happening in chemical equations, we can start to look at the definitions of the terms that we need to use. So as a brief reminder, we're going to have a look at the animation we looked at earlier, and this time have the half equations underneath the animations as well. So we have the two bromide ions and the two chlorine atoms joined together as a molecule, and the electrons exchange, and we end up with 2Br minus forming Br2 plus 2E minus, and Cl2 plus 2E minus forming 2Cl minus. The bromides lost the electrons and the chlorine gained them. Now the definitions that we need to know, there are 4, and the first one is that a species that is oxidized loses electrons. Now this is the oil part of OILRIG. Now looking at our diagram at the top, which species has lost electrons? Well, the species that loses electrons is the bromide ions. The second definition is that a species that is reduced gains electrons, and that's the rig part of OILRIG. Which species has gained electrons? Well, the species that has electrons being added to them is the chlorine, the Cl2. The third definition is that a species that provides electrons is a reducing agent. Now this is a little bit of a new term, a reducing agent. What this means is that this is a species that causes something else to be reduced. So this is something that gives electrons away and allows another species to be reduced, to undergo reduction. In this scenario, which species is providing the electrons or losing electrons? Well, in this it is bromide. The final definition is that a species that removes electrons is an oxidizing agent. So this is something that takes electrons from something else, allowing that other species to lose electrons and be oxidized. So in this scenario that we've got, what is doing the removal? What is taking electrons away? Well, the thing that takes electrons is the Cl2. So we can see here that bromide is oxidized and acts as a reducing agent, whereas the chlorine is reduced because it gains electrons, but it acts as an oxidizing agent. Now the thing with this is to make sure that you think like a chemist and not a parrot. That might seem a bit strange, but while it's really important that you learn those definitions, and you could be asked in the exam, define oxidizing agent, and you would have to give the answer in terms of electrons, like on the previous slide, it is really important that you're able to think through the chemistry that's present and not just be a parrot spouting out definitions. So learn the definitions, but make sure you can apply them. So to recap, if we take these two half equations, currently unfinished, what we can do is we can complete them to make them chemically balanced, showing the electrons, and then we can recombine them to get the half equation at the end and identify whether we've got oxidizing agents, reducing agents, and oxidation and reduction processes. To do this, the first thing we're going to do is to balance our half equations. And initially, you must make sure you've got the right number of atoms on each side. So on the chlorine reaction, we start with Cl2. There are 2 atoms joined together to form the molecule. And on the right-hand side, we're forming chloride ions. But because we start with Cl2, we have to make 2Cl minus. The next thing to look at are the charges. We have a 0 charge on the left-hand side, and we have 2 minuses on the right-hand side. Now we can only balance this with electrons, which are negatively charged, and we have to think about where they go to balance the charges. So we think about this mathematically. 0 equals -2 is incorrect. We need to make sure we've got some electrons in there. Now electrons are negative, so we can only balance this using negative charges. Well, 0 minus 2 equals minus 2 would be correct, and that tells us that the electrons have to go here. We can tell that chemically as well, because we've got a negative charge or two negative charges appearing on the right hand side, and they can only appear due to electrons being added to the chlorine in this particular half equation. To repeat that for the bromide, we'd follow the same steps. We start off with one bromide, and it's forming Br2. Well, we therefore must have two bromides to begin with to form Br2. 2Br- forms the neutral bromine, so these negative charges that the bromide has currently have to go somewhere. The bromides lose them, and they are shown as a product. So I'm doing this in a slightly different order to the chlorine to show you there's two ways of looking at it. Once you've put your electrons in, double check that your charges are balanced to make sure you've got the right number of electrons on the right side. So two negative bromides would have a charge of -2 equals 0 for bromine molecule, -2 for the 2 electrons. So -2 equals 0 minus 2 is mathematically correct, and therefore that shows our half equations must be as well. Now, the next thing we have to do is to combine these to form a full ionic equation. Now, we've worked from the ionic equation to the half equations, but you need to be able to go the other way as well. So what we're going to do is we're going to combine the two half equations, and we're going to cancel out anything that appears on both the left and the right. So what we're going to do is take everything that is on the left hand side of both equations, and we're going to write them together. So Cl2 plus 2E- from the top equation plus 2 bromides from the bottom, and that's everything on the left of the arrow for both equations. Put the arrow in, and then we're going to put everything that's on the right. So 2 chlorides plus a bromine molecule plus 2 electrons. So we've combined the half equations. Now what we can see here is we're going to combine both the left and the right again, and like we did the spectator ions, we're going to see if anything is on the left and on the right the same way. Cl2 appears on the left hand side but not the right. 2E- we can see appears on the left and on the right. So what we do is we cancel those out. Now just double check that there's nothing else that appears on both the left and the right. 2Br- is on the left but not the right. Br2 is on the right but not the left. Therefore, that is our ionic equation. Cl2 plus 2Br- forms 2Cl- plus Br2. And as long as all of the electrons have cancelled out, that's the ionic equation. So now it's your turn. Have a look at the half equations on this slide, and I'd like you to A, complete the half equations and form the ionic equation, so that is adding electrons, balancing, and then combining and cancelling to form ionic equation. And then B, I want you to identify the species in each case that has been oxidised, the one that's been reduced, which one is the oxidising agent, and which one is the reducing agent, and label those with the labels I've given you on the screen, the same as I did on a previous slide. So answers. First of all, copper 2 forming copper, and then we have magnesium forming magnesium 2+. Copper 2+ needs to gain 2 electrons to form neutral copper. So we have +2 minus 2 equals 0, just to double check the maths there. And then the magnesium forming magnesium 2+, well, the magnesium needs to lose 2 electrons in order for the magnesium 2+ to form. Now, we're going to combine these to form the ionic equation. And we can see that we have 2 electrons for the copper equation, and we have 2 electrons for the magnesium. So magnesium produces 2 electrons and copper takes both of those 2. So we've got a balanced situation at the minute. We can cancel out the electrons straight away, and our equation will end up being Cu2+ plus magnesium forming Cu plus magnesium 2 plus. Identifying the oxidation and reduction processes. Well, we can see that the copper 2 plus is gaining, and therefore copper 2 plus is being reduced. The magnesium is losing electrons, and therefore the magnesium is being oxidized. Remember, oxidation is loss, reduction is gain, OILRIG. And then something that is reduced allows something else to be oxidized, so it's always the opposite. So the copper is reduced itself but acts as the oxidizing agent, and the magnesium, as it is oxidized, causes the copper 2 plus to be reduced, so the magnesium is the reducing agent. Question 2, K forming K plus. Well, it would be K plus plus E minus. The potassium atom loses an electron to form K plus, and we have 0 equals plus 1 minus 1. Mathematically, that is correct. And then F2 forming F minus, slightly difficult here. F2, 2 fluorines on the left, so we need 2 fluorides on the right hand side. And for the fluorine molecule to form fluoride, it needs to gain electrons. So we have 2 Fe on the left hand side. Now, to combine this, we need to compare the two equations. A potassium atom loses 1 electron, but a fluorine molecule needs 2 electrons. Now, what this tells us is that we would need 2 potassiums, 2 times that potassium equation, in order to give us enough electrons to allow fluorine to form fluoride. So to combine these 2 potassiums plus F2, cancel out the electrons, forms 2K plus plus 2F minus, and that's the Ionic equation. In terms of oxidation and reduction, the potassium is losing electrons, so the potassium is oxidized. The fluorine gained electrons, and therefore the fluorine is reduced. And as we said before, if something is oxidized itself, it is a reducing agent. So the answers are there. Question 3, H plus forming H2. We need 2 H pluses, and then we need 2 electrons to cancel out those charges. Plus 2 minus 2 equals 0. And lithium forming lithium 1 plus. Well, lithium has to lose an electron in order to form a positive ion, so we have Li forming Li plus plus E minus. We can see that we have 2 electrons needed by the H plus, but 1 lithium only provides 1 electron, so we would need to times the bottom equation by 2, so 2 lithium atoms would form 2 lithium ions and 2 electrons. We can then see that we can cancel out the electrons because there's 2 in each one, and therefore 2H plus plus 2Li forms H2 and 2Li plus. Doesn't matter what order you put those in as long as they're on the correct side, left or right. So our hydrogen ion here has gained electrons, so the hydrogen is reduced, and the lithium has lost electrons, so that is oxidized. And again, if something is reduced, it is itself an oxidizing agent, and if it's oxidized, it's a reducing agent. And finally, we have aluminium forming aluminium 3 plus. For aluminium to form aluminium 3 plus, it has to lose 3 electrons, so the electrons go on the product side as they've been lost from aluminium. An oxygen molecule forms oxide ions. We have O2 on the left, but only O on the right hand side, so one O2 molecule forms 2 O2 minus oxide ions. And then electrons, this one again can be a little bit tricky. O2 is neutral, but we have 2 minus ions, so that's 2 times minus 2. So we actually have minus 4 on the right hand side. So our electrons have to go on the left-hand side, because the O2 molecule has to gain electrons to turn into negative oxide ions, and mathematically we can see that that is correct as well here as well. So overall, this one is a little bit more complicated. Aluminium produces 3 electrons, but an oxygen molecule needs 4. So where does the extra 1 come from? The extra electron can only come from aluminium. So we could start with 2 aluminium atoms, but if we started with 2 aluminium atoms, we would produce 6 electrons, and the oxygen only needs 4. There would be 2 left over. All of the electrons that are produced have to be used. So we need an equal number of electrons from one half equation that are going to be used in the second. We are looking for the lowest common multiple. Of the 2 numbers of electrons. And the lowest common multiple is 12. So we would need to start with 4 aluminiums, and that would give us 12 electrons. And we need to start with 3 oxygens, and that would give us 6 oxides. And at that point we do have 12 electrons on the top equation and on the bottom, and that means that they will cancel out. So our ionic equation for this one is 4Al plus 3O2 forms 4Al3 plus 6O2 minus. The aluminium has lost electrons, so it is oxidized and is therefore a reducing agent, and the oxygen molecule has gained electrons, so that's the reduction, and is therefore an oxidizing agent.